Hi, it's Mohammad Sadiq Rahman. So today I'm just recording my understanding on assignment number 6, that is some optimization problem that is based on stochastic gradient descent algorithm. So it's a very efficient algorithm that just minimizes the cost functions, and it is somehow different from gradient descent in that sense that is in gradient descent algorithm. The algorithm includes all the training examples, but in the stochastic gradient descent, it just takes a small subset of the training examples to update the parameters so that the cost function is minimum. So we're just going to detail of this algorithm. At first, we're just importing all the necessary functions from scikit-learn and the splitting of this dataset in training and testing samples, and in for plotting the graphs, we are just importing library and NumPy, so on. So at first, we are just generating some values. So we'll just our problem will be with the with some weights and height relationships. So as x variable, we are just taking some random um, weights between 40 to 120, and we're taking 100 samples. So np dot random the rand it will generate an array that that is from the lowest value is 40 and the highest value is 120, and it will take 100 samples. So the size of this array will be one-dimensional array with the 100 elements. So if you print this, we can see that it starts from 400 and it ends up to 119 as it is sorted. So this is this array is already sorted in as ascending order, and we are just assigning some corresponding heights here. And for height assigning, we are using these functions. And here this item is nothing but the values of this x, and it is divided by 30. So as the maximum value is 119 or 120, so this first term will get up to 4, and now we are adding some another parameter that will give us some integers between 2 and 3. So the maximum value of these first two terms will be 4 plus 3, that is 7, and the third term that is coming from it will generate some random values from 0 to 1. So the maximum output of this three term summation will be 8, whereas the minimum value will be that is 40 by 30, that is 1.33, and this minimum value is 2, so 3.33, and this minimum value is 1, so this is minimum value is 0. So actually the value of this height will the minimum value will be 3.33 and maximum value will be 8. And we can verify this if we print this the value of y, there is nothing value less than 3.3 and there is no value greater than 8. So in between this 3.3 to 8 feet height, we're just assigning this value with the 100% of different weight ranging from 40 to 120. So the weight range is 40 to 120, whereas the height range is from 3.33 feet to 8 feet. So this is quite natural and quite realistic, some values. Now we're just plotting this data in x and y axis. In x axis it is a weight, and in y axis it is height. So we are randomly plotting this data for our visualization. Now we want to this is our data set. We want to split it in training and testing data set. So we are assigning test size is 0.1. That is in total there is 100 number of values in x-axis. So 90 values will be used for training purpose, and the rest of the 10 values will be used for testing purpose. And random statistical 42, that does mean in each iteration or each training, it will take the same number of same training and test data set for each iterations. And we are just want to model this data set with a linear regression model. It is y equal mx plus c. So there are two main parameters. That is the gradient of this line, and this is the constant term. This is the y-intercept. And we want to minimize the error. So the mean square error is can be found by this way, where n is the number of samples, and yi is the true level, or this is the actual y value or actual height, and y1 hat, this is the predicted value from this model. and we just want to take this error. This is the difference, the error, and we want to minimize it. So this is squared error mean. So now we're just defining the mean square error function. This is also called a loss function that will take two parameters. That is the prediction value, that is y hat, and it's the actual value, that is y. And the error is nothing but the difference, and squared error is the square function, and we're taking the mean. So this loss function will return us the mean squared error value. And as I was telling earlier, that is the model equation. Y hat is the model value, mx and c. So the stochastic gradient descent system that takes the small subset of training data set, and each time it just updates the parameters. Here the parameters are m and c, and by updating the parameter, it just wants to feed the data. So the mean squared error, we want the minimum value. That's why we are just differentiating it with these two parameters m and c, and we just get this equation from some derivatives. And whenever we'll get this, n is the best size, that is how many samples we'll take each time, and the parameters can be updated by this value. That is m equal, this is the updated m, this is the previous m minus learning rate eta, and this derivative value, and similarly the constant terms will be updated accordingly. So now if we whenever we'll just get these values, we can just our stochastic gradient descent algorithm works in this way. So we're just taking the indices, and we're just doing this operation, that is dot product of this parameters with the x batch value, and plus c will get the predicted value, and we'll calculate the error, and we'll update these m and c, just calculating the gradient value, that is the gradient of m and gradient of c. This is nothing but these two equations. It is 2 by batch size, error times x batch, and summation. This is the gradient m, and for gradient c, this is 2 by n and summation of error. 2 by summation of error, and then whenever we'll get this value, we can update the parameters by this equation, that is new m equal previous m minus learning rate of gradient m, and new c will be c minus learning rate of gradient c, and this stochastic gradient descent function will return me the new updated gradient and new updated constants. And whenever we'll just start our visualization with some random parameter, that is m and c, we're taking some random values from 0 and 1. Here it is the random generated gradient is 0.73 and c is 0.2, and we'll just plot this graph, and it doesn't fit our actual value. So our target is to update this m and c so that it just perfectly fits this data. So we're setting the learning rate as 0.0001, batch size is 16, and we'll take total 10 iterations. And whenever we'll just pass these two values in the stochastic gradient descent function, it will return us some updated m and c. And with this m and c, we'll just we'll find our predicted value, and we can also calculate the loss function. This is the predicted value and the actual test value, and we'll just print the iteration. That is, at first iteration the loss was higher, but with the consecutive iteration, the loss is getting lower and lower, and it finally came up to 2.29. So this is nothing but the outcome of the updated m and c value. That's why the model is learning very well, and it is just fitting the data very well. That's why the loss value, that is the difference or error, is getting minimized. So if we want to plot these values, that is number of training data set, that is here 10, and this is loss function that started from 300 or 0.301 and ended up to 2.29 actually. So with the progress of training iteration, the error is getting lower. That is the final. That was our target to model this data set. And whenever we got our final M and C after 8th iteration, we can plot this data, and actually indeed it just fits our main data set. And that's how stochastic gradient descent, it just takes some batch size, and it doesn't include all the training samples at a time. It just takes some batch wise subset of data, and it just trains the model so that the computational speed is higher and it doesn't take so much memory, and actually the output and ultimately irrigation line is a very satisfactory result. Thank you. Thanks for this video.